It's entirely possible we could get the cost per kilogram on the accelerator side alone down into the neighborhood of, $10 a kilogram. When you open a new frontier and humanity's colonizing the solar system, how much would it be worth to have 1,000 new Americas? You can't put a number on it.
Growing up in human space flight and also just looking at traditional rockets, this type of system really changes the paradigm.
There's still a lot of technical challenges ahead of us, but I don't think these are problems that are unsurmountable.
By the way, for everyone listening, there is going to be a quiz after this with all the equations and numbers that Nato just rattled off. So, hello everyone. I'm Jon Gowan, managing partner of Kickstage Ventures, a relatively new venture capital firm. My background is actually in aerospace engineering. Started off working at NASA, have over 20 years of experience at NASA Johnson Space Center, working in mission control as a space shuttle flight controller, also doing strategy and partnerships, working with SpaceX and Boeing on their vehicle development, and then finished my career as a division manager in a lot of areas I think are relevant to Longshot, hypersonics, trajectory analysis, GNC type of work. But in addition to that, I've got a long financial background as well, and I'm trying to merge my passion for aerospace with my passion for investing now, and I get to talk to cool companies like Longshot. So, Nato, you want to tell us a little bit more about yourself?
Yeah, thank you. So I'm Nathan Saichek. Everybody calls me Nato. I'm a CTO at Longshot, and I basically graduated with a degree in aerospace engineering back in 2007, and then got startup pilled, moved to Silicon Valley, started working for startups, building satellites, worked for some biotech companies, doing robotic automation stuff, and then moved back into aerospace and again, built more satellites and rockets at a couple of other companies. So just trying to be a broad generalist engineer before my co-founder sucked me into building giant space guns. And we've been doing that for the past 4.5 years. It's been a fun learning opportunity.
Yeah, absolutely. No, fantastic background. And really looking forward to this conversation. So when I first came across Longshot, first thought in my mind is, haven't we tried this in the past? I think I've heard of other mass accelerator programs. And after talking to Mike, I guess it dates back to even World War II, Nazi Germany timeframe. But can you tell us what's been tried in the past? Why is maybe now the right time to try this again?
Sure. It goes back even farther, Jules Verne, from the Earth to the Moon. But yeah, I think the main thing that has changed is the economics. When we were first developing rockets and we were first trying to go to space, it was, on the back of trillions of dollars of investment between, the US and the USSR, basically developing, ballistic missiles for, delivering nuclear weapons. And when you have collectively as a society invested that much in a technology, it's really easy to see, we can take this technology and we can just modify it slightly and now we can go to the moon. The reason people didn't develop like super guns for lobbing nukes is because basically you can't hide a super gun. You can't put it on a submarine. And while gun systems in general have among their characteristics, it's really nice, is that the marginal cost, the cost per shot is really low. Nobody cares about the marginal cost per shot for ending life on the planet Earth, right? And also in general, governments who are doing giant national prestige projects also generally don't care that much about cost per shot. They're fine spending a few $1 billion to build a giant rocket to send people to the moon, or send people to a space station, or all kinds of cool prestige projects. But in the past 15, 20 years. The thing that has changed is people have found commercial applications in space that are meaningful, and where being able to get more stuff to space cheaper starts to matter more, and people have started, noticing the commercial aspects of space. So, the marginal cost of putting a satellite up does matter, and so people have spent a lot of effort on optimizing rockets for operational purposes and, cost per shot purposes, and, reuse is a huge thing. And so those are all things that absolutely should be done and are important to make space a more accessible environment.
Yeah, and I spent my whole career in human spaceflight, right, where you worried about the astronaut health, and this isn't the type of system that's ever going to be appropriate for human spaceflight, right? I mean, we're the space shuttle program. We limited the Gs to about 3 Gs on ascents. We throttled back the engines to make sure we stay below 3 Gs. And I think you guys are hitting
300.
300, 500 Gs. Right. That may be a little sporty. But, things like prop tanks and even electronics and other things don't really care too much about 500 Gs. Modern electronics are all designed for that, right?
Yep, they're all fine. There will be a bunch of things that that when packaged correctly can be sent to space in those G environments. Resupplying a space station could be done. Getting up, food goods and water and packs of solar panels or feedstocks, things like that. Those would all work great. But yeah, we're never going to send people up.
Well, I had to really change the way I thought about this as well, because again, growing up in human space flight and also just kind of looking at traditional rockets, they're designed to be light mass systems, right? You always want to minimize mass on the payload, minimize mass of the actual vehicle. So structural loads can be an issue if you're not, keeping the rocket pointed directly into the velocity vector, all those sorts of things. But tell me about how this type of system really changes the paradigm, because it took me a fat minute to really realize, hey, in this system, mass is your friend, right? That means higher ballistic coefficient, cutting through the atmosphere.
There's two things that sort of play into it. Is one is like, we're planning on the system, if we launch at something close to orbital velocity, even if we're only half orbital velocity, say 4 or 5 kilometers per second, the dynamic loads on the vehicle are going to be
enormous.
Literally 1,000 times greater than you would typically see on a rocket.
Right.
And so, I've helped build rockets out of sheet metal, and 16th inch aluminum is, that's your friend on a rocket.
Right.
For our system, we're going to be closer to a bullet than to a rocket. If you're looking at a rocket and you looked at our system, you'd say that thing is a lot like a bullet. If you looked at a bullet and then you looked at our system, you'd say that thing's a lot like a rocket. So bullets are actually like fully monolithic, and we're going to be hollowed out. And but we're not hollowed out as extensively as a rocket. So rather than 16th inch of aluminum, we're like ½ inch to an inch of stainless steel plate, which is real. It's a real amount.
Right.
It's a significant significant structure, but it's not solid. It's not monolithic. There's plenty of room inside to accommodate all kinds of stuff, avionics and payloads and things like that. At the scales that we're talking about. Again, because ballistic coefficient is your friend and you want a lot of mass behind every, square centimeter of a vehicle, that means your vehicle has to be pretty long to put enough mass behind it to punch through the atmosphere, which means that your vehicle has to be pretty big because you want it tapered at a particular angle to have good aerodynamic characteristics. So basically, we think that the smallest space launch system that we could build would have a muzzle diameter of something in the neighborhood of 3 meters. And the vehicle itself would be basically a half cone of that radius with something like between a 5 and 10 degree half angle point to it. And so that's a pretty large vehicle. It's like 15 meters long and ½ inch stainless plate down a large, most of the body will be thick stainless plate. And then we'll have a payload at the back, but and the interior filled with, basically payload and some sort of probably a kick motor to circularize the orbit. But yeah, the whole thing, we're going to try and pack it as densely as we can. We want the thing to be, 1,000 kilograms per cubic meter. We want it denser than if it was filled with water, if we can do that, which means we're not afraid of having, the nose needs to be a little bit thicker stainless to accommodate the bending loads at the nose. Okay, we'll make it an inch thick stainless plate. We're okay with that. We also expect we'll be able to reuse most of that structure, so we're not throwing away 10,000 pounds of stainless every time we take a shot. We expect to be able to reuse that. But it is a different way of thinking about things. From a traditional rocket, or even a high performance aircraft.
Instead of aluminum and composites, you guys are talking about steel and tungsten, right?
Right. Yeah. We may have like a tungsten nose just to handle the aero loads basically there. Entirely possible. We'll see how things play out. I think a lot of this is because it's completely unprecedented. I think at the scales we're talking about, people have fired things faster than this from like gas guns, as I'm sure you know. But not, not something that's a meter or more in diameter.
Right.
And so making those systems operable and controllable and even observable, like figuring out what happened to this projectile after we fired it from the barrel and it traversed some distance through the lower atmosphere. How are we going to get data off of that and figure out what happened to the heat shield, that prototype heat shield we put on the front of it?
Right.
Is going to be a fun challenge. I don't know. We have all kinds of fun ideas about how to do it, but we can get into it if you like. But yeah, I think there's that big architectural shift is the real thing.
Right.
Yeah.
And like you said, I mean, even a bullet from a traditional gun, it's not going, hypersonic speeds, right? We're not hitting Mach 10, Mach 20, but NASA does have light gas guns. I'm familiar with that from my time at Johnson Space Center, the White Sands test facility. They have hypervelocity impact testing capability for MMOD testing, micrometeored orbital debris. And so it's a two-stage light gas gun where they do get up to those, Mach 20 type velocities. So maybe talk about, why not just scale that type of system up, or talk about some of the other systems that have been tried. This isn't a rail gun, but maybe talk about that, or electromagnetic mass accelerators.
Yeah, the historical thing that people have done to get projectiles up to that speed is like a light gas gun, two-stage light gas gun. You've got some gas mixture that combusts, accelerates a piston that then squeezes another gas mixture that typically mostly hydrogen, I believe, and that then punches through a burst disk and is released at ridiculously high temperatures and pressures onto the back of the projectile that then is driven down the barrel and emerges at 10 kilometers per second or whatever it is that the design velocity. Part of the reason it makes sense is that those systems have to have very thick barrels to accommodate the colossal pressures that they're handling. And the projectile itself has to be basically a monolithic slug of material to handle the G-loading that it is subjected to. Neither of those things are conducive to an inexpensive, useful space launch facility. So rather than having like a single giant injection of energy at the beginning of the system, we plan to distribute the energy down the length of the barrel. And rather than having, something like 100,000 Gs of acceleration at the beginning, we will have something like, a few hundred Gs of acceleration, and we'll just try and keep it constant down the length of the barrel. People have tried to use railguns and other similar systems. I think, again, these are designed to accelerate relatively small masses, something the size of like an artillery shell or something like that. And there have been billion-dollar projects to build railguns that have, gotten them supersonic or maybe slightly, barely into the range of hypersonic. But we want to be going not Mach 5, but, Mach 20.
Right.
Not, 2 kilometers per second, but 6 kilometers, 8 kilometers per second. And so if we're looking at heritage, it's sort of hard to justify how are we going to build something that can send something that we think from a vehicle design perspective, this vehicle has to be colossal. It has to be meters in diameter in order to get a significant, payload into orbit. And so squaring that with like an electromagnetic accelerator doesn't really make sense. That seems like it would have to be a really colossally huge system, and the capital intensivity of it. You know what? If somebody happens to have an extra $50 billion they want to give us to play around with that, I think maybe you could do something like that. But I think it's
your capital raise requirements for this current round, right?
It's already hard enough, at least for us. It's hard enough to raise capital for the giant space gun without it also being like a giant rail gun, which is going to be has a whole different set of challenges associated with it. So we're trying to keep it as simple as we can.
Yeah, that makes sense. I know we've talked about this in the past. I'm of the opinion that the super cannon, building that's actually the easy part. I mean, I know it's still challenging. I'm not trying to minimize it, but the projectile, I think, is going to be challenging flying through that environment. But, you still have some unique challenges with the cannon and some things that I was curious about just in terms of, how you prevent the projectile from contacting the walls. How straight does the barrel of the cannon have to be? Is it laser straight? And is it just, the walls have to be that straight, or, the rails within the cannon?
One of the things we've worked on is we have a 6-inch, prototype cannon system. and we have two rails that run down the length, and the projectile rides on those rails, and there is a small gap around the perimeter that basically, I mean, it does reduce the efficiency of the system. Gas does slip by the projectile as the projectile is traveling down the barrel. We thought that was a worthwhile trade to make, and I'll try to explain a little bit about it. So the barrel itself, we want to be inexpensive. We think that's going to be a huge, capital investment to build this giant barrel.
12 kilometers worth of steel.
Right, exactly, at 3 meters in diameter or larger. And so we don't want to have to make that thing, super pristine, mirror polished walls or whatever, to have a perfect seal along the edges and have it be, again, laser straight the whole length. We want to make it so that the barrel can be cheap, and then we can have a relatively low mass subsystem, the rails, be more precision and aligned properly. Part of the way that we design and build the system is we create basically a virtual center line that runs down the length of the barrel, to which we mount the rails. And so we have jigs and fixtures that basically hold the rails around a little cross that is a hole. There's a hole in the fixture that is the shape and size of a cross, and the size of the cross is such that the vertical and horizontal gaps are the size of the acceptable tolerances of our whole system. So we set those at, say, like a 1/16 of an inch. And so then we can put these jigs down the length of the barrel, and we can sight down with a telescope, and we can see like, oh, jig number 17 is off. We need to adjust that one. And then the jigs are mounted inside the barrel, and so we adjust them relative to the barrel. So the barrel sort of floats around, and the barrel's going to be egg-shaped. It's been sitting out in some, boneyard for years. Right. The barrel's going to be egg-shaped and floppy and weird, and it's just going to
impact it in terms of swelling or whatever. Yeah.
All kinds of stuff. Yeah, heating and cooling. So as long as we keep the rails perfectly aligned, then those are the bearing surfaces that the projectile rests on. We have these shoes that rest on the rails. And so as long as those are all aligned, then the projectile should see, in theory, should be able to, we don't want to impose extra loads on the projectile. It's going to be getting lots of loads from behind, from the gas injections and stuff. And we don't want to have to shake it around as it moves. The shoes, for our current systems, don't have much suspension, but for the future, we're also planning on the shoes having some small amount of suspension, to give them basically some really heavy-duty springs that are constantly feeding material into the rails, because we expect the shoes to degrade as we travel down the system.
Yeah, is that creating a lot of friction, having those shoes? I mean, I'm just imagining this projectile going, Mach 10, Mach 15, and, riding rails. Talk about the friction associated with that.
There may be some friction. We expect that the shoes, they're made out of plastic, and that they will basically ablate away as they go. And, they're high density polyethylene or Teflon. We've played around with a few different materials. It's hard to quantify the friction that they are causing, because we haven't been able to measure it. It's been so low, we haven't been able to measure it. Yeah. So it might be the case that when we build much larger systems, that will become an issue. But so far it has been.
Because you're up to Mach 4.5 right now, and you're
4.2.
4.2, but not seen as an issue yet.
Right. But this is a relatively short accelerator that we've built so far. Once we have something that's, kilometer long or something like that, maybe we'll see more degradation, maybe we'll see problems. I think part of this is, again, it's unprecedented. In some sense, this is what those light gas guns already do. They have, Sabot systems that have high density polyethylene, and they're like pressed into the barrel with a hydraulic ram, and then they ride down, the rail system inside the barrel on high density polyethylene. So we did crib from existing light gas guns, where, again, the drag doesn't seem to be so much of a problem that it causes performance issues. So hopefully, we sort of expect we'll be in the same neighborhood. I think that answers most of the question about alignment. Something like a 1/16 of an inch in the barrel can float around. There is a thing about the gap around the perimeter. So on our 6-inch gun, we have something like a 1/8 inch gap around the perimeter of the projectile to accommodate basically the water transmission pipe being crappy. For larger systems, we'll probably have a physically it'll be a larger gap. It might be a 1/4 inch or 1/2 inch. But the ratio of that perimeter gap area to the area of the vehicle will be much smaller. So, you can kind of model it as though you're firing a projectile that has a hole in it, and the size of that hole is represented by the area of the gap around the perimeter. And so that hole, the fraction of the projectile that has the hole that lets gas through, will get smaller as we build larger systems. So we expect that to be less of an issue at the larger sizes as well.
Okay. I think you guys have described the back end of the projectile as being tapered because once you reach a certain velocity, you got a Mach up there.
Yeah.
Okay.
So we've got,
Nice.
This is like one of our 6-inch projectiles.
Okay.
You can kind of imagine, something like that.
Gotcha. So the gas is being side injected, and since you've got the tapering, it's continuing to accelerate.
Yeah, it squeezes the tail to keep you moving when you're past, where a traditional gun, the gas, there's a pressure curve that drops off as you're traveling faster.
Somewhere around Mach 5, I think, or something like that.
Yeah,
That it starts to become ineffective unless you have a side injection system.
It's a 2A0 over gamma -1. So the speed of sound of your fluid doubled divided by gamma -1 is the maximum possible theoretical top speed of a gas gun. So the speed of sound of hydrogen is 1,270. Double that, you're like 2,500 meters per second. And then gamma for hydrogen is 1.4. So subtract 1.4. So basically it's like dividing by 0.4. So it's basically doubling. So you go up to like 5 kilometers per second is the maximum possible theoretical you could ever get from a hydrogen gas gun. In practice, you cut that number about in half, or a little bit less than in half. 40% or so of that number is what you can actually get in practice. So we go from 5 kilometers per second down to like a little bit more than 2 kilometers per second is sort of like practical. So how do we get faster than 2 kilometers per second? Well, the tapered wedge gives us that sort of like speed multiplier effect, where if we've got a 5-to-1 taper ratio, we can have the gas coming in at if the maximum speed that the gas could accelerate something is like 2 kilometers per second, we've got a 5-to-1 taper ratio. That means that our top speed is something like 10 kilometers per second. Hand wavy, all things being equal, assuming, inside the barrel drag isn't excessive, assuming that, other, friction on the surface doesn't kill us in a variety of other ways. There's a bunch of other caveats there, but that's the fundamental idea. And if we can't make it all the way to 10, hopefully we can make it to 6. And if we can make it to 6, we think we'll, even if we made it to 5, we'd be fine. Anyway, there's a bunch of fun stuff we can talk about there.
By the way, for everyone listening, there is going to be a quiz after this with all the equations and numbers that Nato just rattled off. So let's talk about the projectile. Because like I said, in my opinion, once it exits the cannon, that's when things really get interesting, because now, even if it's Mach 10, I know you guys have aspirations of 7-8 kilometers per second orbital velocities, and maybe you'll get there, but I think whether it's Mach 10 or Mach 20, it's going to be sporty when it exits that
barrel
muzzle. So you've got max Q,
right off the bat,
dynamic pressure. Right when you exit, you've got basically you're traveling so fast that air molecules are ripping apart, and you got this plasma field around, which creates enormous heating. So you're going to have peak heating right off the bat.
Yep.
You're going to have potential controllability concerns associated with that. I think you're looking at maybe a flat plate that's going to generate lift. So you're going to generate a whole lot of lift right when you're coming out, and you need that lift because you got to get out of the atmosphere and not hit the side of a mountain, because you got a completely horizontal barrel system here. So talk about all those challenges.
A whole bunch of challenges. Yeah. People have built heat shields to handle the types of heat loads that we expect to encounter. They technically have made heat shields for that thermal environment before. The Galileo spacecraft, we've talked about this. The Galileo spacecraft, when it re-entered, had similar heating at much lower dynamic pressures.
And that survived for a lot longer than people anticipated, right?
Yeah.
It went pretty deep into the atmosphere.
Yeah, and it had much less ablation of the front surface, actually, than they were expecting as well.
Okay.
I think they made it something like 14 inches deep ablator on the nose, and it actually only went back like 6 inches.
And that was going like 50 kilometers per second as opposed to 8 kilometers. It's super easy.
Right, by comparison, in some sense, yeah.
But the atmosphere, Jupiter is quite a bit different as well. So maybe not an apples to apples comparison.
It's not the same. There's a few other ways in which we're much worse off. One is the atmosphere is much denser. We'll be like more than 1,000 times more dense than the Galileo probe at the outskirts of Jupiter's atmosphere. And so the dynamic pressures will be much, much higher, a couple hundred times higher than the Galileo probe encountered. And when you start doing, the analysis on, reentry vehicles or hypersonic vehicles, there's a big deal made about like the nose radius. And the Galileo probe had a virtual nose radius that was several meters in diameter. I mean, it didn't actually round all the way out. But it was trying to slow down, nose radius, a large nose radius, gives you at least in theory, it makes it much easier for the shock to be detached.
Detached bow shock type of thing.
Exactly. Yeah. And we are trying to minimize drag, not maximize drag.
Yeah.
So we are deliberately going to have as small and pointy a nose as we can get away with. And so we will end up with an attached shock, which will have worse heating. It'll have, worse ablation characteristics, probably. Again, as far as I know, nobody has built a heat shield of the scale that we're talking about, something, like, meters in diameter and, to be traversing this environment. The only thing that in some sense saves us is that heat shield for the Galileo, lasted for several minutes in a crazy environment. And we only have to last for literally 5 seconds. Once we, ascend through
You'll get out of the appreciable part of the atmosphere in the first 5 or 10 seconds.
Right. Like you said, we start off at max Q and max heating, which means right off the bat, all of our loads are dropping, our heat's dropping. We just have to survive that, that initial, blast furnace plus hydraulic ram crusher environment for a few seconds, and then we're in the clear. And we did mention, the controllability in that environment. Again, I don't, people who have historically tried to fly things at these speeds have not tried to fly them in these dense environments. And so controllability is a guess in some sense. It's really hard to analyze. We can take models that exist and try to extrapolate them out to these domains and say, yeah, we're going to try and hold this attitude.
RCS isn't going to work at that type of dynamic pressure.
Yeah.
Control surfaces are going to have limitations.
There's some things where, so I'd say we have one maneuver, which is when we emerge from the barrel, we expect to be, we'll start off at a slight angle of attack, and we'll use that to ramp up to an ascent angle, something like 10 degrees, 15 degrees. So we just have to do that single ascent, and then we level off. So the only maneuver that we're doing is, if we emerge from the barrel with a stable angle of attack at a 2-degree angle of attack because of the location of the center of pressure and the center of mass, then after 3 seconds of flight, we need to change that either by having control surfaces that
body flap or something.
Body flap, or by physically moving a large mass inside the vehicle and change that. We don't think we'll have much in the way of external control surfaces. It's certainly possible. We might have 4 little drag rudders or something to do trim. We've talked about potentially using RCS just for roll control, not for any other thing, because the only sources of external forces that are going to cause roll will be perturbations on the vehicle due to this part of the heat shield ablated a little bit faster than expected. And so we just have to correct for that small deviation, again, for a couple of seconds. Once we're out of the thickest parts of the atmosphere, that all gets much easier as we go along. We get higher in the atmosphere and the heating gets lower and everything like that. So I don't want to make a strong commitment. We're definitely putting RCS jets on it, or we're definitely going to have quad, drag rudders on this thing. What we're going to do is we're going to build something that shoots stuff at 4 kilometers per second, and we're going to fire it like a dozen times, and we're going to, measure the results and see how it looks. And we have some ideas. I want to float an idea actually by you, because it's going to be really hard to see a heat shield at 4 kilometers per second after it has ablated, because we're going to be way downrange.
Yeah.
So one thing we've talked about is basically firing the projectile across something like, a couple kilometers of desert, and then having a receiving barrel that's evacuated. That's, something like, again, if our projectile is, say it's a small projectile, it's only 1 meter in diameter. And then we have a receiving barrel that's a couple meters in diameter, and we, punch into this receiving barrel that's evacuated. Then we can image the projectile inside this controlled vacuum environment after we've flown through, this, crazy aerothermal environment, and image the heat shield and see what it looks like before it, crashes into a catch box and obliterates itself. Anyway, I thought that would be a cool experiment to try and run.
Yeah, it's interesting. Imaging the heat shield is going to be critically important for those initial tests. I completely agree. I mean, there's a lot of airborne assets that we've historically used at NASA for reentry vehicles as they enter the atmosphere, kind of looking at the IR spectrum and looking at the vehicles that's coming down through the plasma region. And when it gets closer to the capsule splashing down, right? We have airborne assets kind of doing some imagery to.
Airborne. When you say airborne assets, you meant airborne instrumentation.
Well,
assets.
yeah, like
Okay.
we'll have
Yeah.
NASA aircraft flying around with instruments on board, imaging the vehicles that's coming down.
Oh, cool.
And we'll have ground-based cameras as well. So yeah, I think some of those, super fast cameras are going to be really, really important to capture the dynamics. And by the way, it'd be like your best marketing material ever. Just kind of seeing this thing as it exits the muzzle of the cannon. But yeah, I mean, you bring up a good point, right? SpaceX had a lot of success by rapidly iterating, and that was very unusual for the aerospace industry to have a rocket failure and then a few months later just try again with some design changes. You guys are going to be able to have an even faster closed loop iteration cycle, because the cannon's going to stay the same. You're just changing the projectile, and I say just changing the projectile. It's going to take a little bit of effort to make those design changes, but yeah, you can probably fire things off couple days later and just make tweaks and see how it goes.
Yeah, we want to make the best, cheapest to operate, highest cadence hypersonic test facility, and we'll use that to de-risk our space launch, technologies. And yeah, when we were doing tests, this projectile was the result of weeks of iteration, cutting material out and taking pictures of high-speed imagery of projectiles emerging from the barrel in variety of conditions. Many of them, I think we fired the 6-inch gun something like 100 and something times, and probably half of those, the projectile came out intact. So, every time it emerged, we were basically trying to reduce the mass of the projectile, so we'd increase the muzzle velocity. So yeah, I think we got a lot of experience with do a test shot, do a debrief, figure out what we need to change for the next one, make the changes. Next day, 2 days later, do another test shot, iterate until you get it right.
Yeah. So you were describing the pitch up maneuver earlier, and then, that basically will get you up to a certain altitude. Then the one maneuver is kind of the leveling off maneuver.
Right.
Okay. Yeah, that makes sense. And I think, you guys are looking at ablative materials, and you can lay the TPS, the thermal protection system, on pretty thick, right? Have a really thick heat shield to survive that initial
and actually, environment. I just saw a thing that made me so happy, because I've been watching videos of people on YouTube making these forged carbon fiber parts which looks so much simpler to make than, wrapped and laid up parts.
Yeah.
Because you basically have a couple of dies, you pack your carbon fiber and your resin in there, you stick it in a hydraulic ram, you compress it, the excess resin flows out, and then you wait for it to cure, you pop it open and your part comes out and works great. And it turns out that the nose cone on Galileo was a molded, chopped carbon fiber, phenolic impregnated, that's how it was fabricated, which made me feel so nice. Because a carbon phenolic heat shield is, if you go by the the numbers that are out in the world, is like $5,000 a kilogram. Super expensive. It's hard to, mostly that's like labor. It takes a lot of work to make a really nice heat shield. But if it's possible to do it with closer to traditional manufacturing techniques, with tools and dies and presses, and we can just make some good tooling for the segments of our heat shield and put them together, that makes me, I don't know, makes me giddy that maybe we can make because the real figure of merit for us is not how good is the heat shield in terms of megajoules per kilogram.
Yeah.
It's megajoules per kilogram per dollar. If we can, we're okay putting on, twice as much heat shield material if it takes a zero off of the cost.
Right.
We're going for a cost optimized system, not a maximum performance system.
Yeah. But as that material's ablating, it creates all sorts of chemical reactions, chemistry that you then have to analyze in your CFD, which becomes very complex, right? And I don't know how far you guys are in that process.
I'll say not very far.
Okay.
Until 2 years ago, really, 2.5 years ago, I hadn't really looked at hypersonic aerodynamics, and thinking about chemistry hadn't really entered my mind. I'd been thinking about hypersonic aerodynamics in terms of gas flow rates and modeling things as particles instead of, pressure waves and things trying to develop the intuitions. And I was talking with one of our advisors, Joe Jewell, who was talking about his, how he was doing gas chemistry modeling. And I was like, wait, what's the deal with the chemistry? How are we doing? What's the deal with the chemistry? When you're working on a rocket, you don't worry about the gas species of the gas around your
But you do for
rocket.
reentry vehicles. So
Right.
Yeah.
So, we had a nice conversation, and I had, thinking about, how does this, the reactions that are going on, you have an incredibly reactive environment right there, where the gas is hitting your projectile and reacting with itself and whatever outgassing off species from that, phenolic and carbon. Crazy amount of chemistry. We've barely begun scratching the surface. We're a small team. We're, a dozen engineers right now. We've been focusing on the mechanical characteristics of getting stuff up to speeds. And now we've started to lean into figuring out, okay, once we get something up to speed, how do we make it work? How do we make it survive?
Yeah. Well, I'm glad you got great advisors like Joe Jewell. I know he's now with the DoD on a special assignment.
He took a demotion.
Undersecretary of DoD Research and Development. So he's doing some great things. But so let's talk a little bit about the separation system as well. So once you get out of the atmosphere, or at least the appreciable part of the atmosphere where the dynamic pressure is low enough, then you can do some sort of separation to release the kick stage to either circularize your orbit or to get you the rest of the way to orbital velocity, which, by the way, my venture capital firm, I intentionally named Kickstage Ventures because I thought it was a good kind of play on words. But when I talk to people who aren't aerospace engineers, they're like, is it Kickstart? And I'm like, no, it's Kickstage. The Kickstage is the last part of a rocket stage to take you in orbit. But you guys will have a kick stage regardless because you have to circularize your orbit.
Yeah.
But you may have to have a bigger either upper stage or kick stage to just even get you to orbital velocity. But either way, you're going to be releasing that system. Why don't you talk a little bit about that?
So we emerge from the barrel, we ramp up off the atmosphere, we coast to altitude, and we expect that the orbital altitude will be a relatively low orbit. We're not going to try and coast 800 kilometers or something. Relatively low orbital altitude, 400 kilometers or something like that. And we will then eject the payload and kick stage. They'll probably come out the back because we want to keep the front of the whole vehicle cohesive And, we don't want to have seams that we're going to have
No
to pop apart.
clamshelling or anything like
Right,
that.
because any seams we have there under those dynamic pressures and heating environments, we expect that they would just erode away and be failure points. So the plan is to have basically the back of the vehicle be able to open up and eject the payload and the kick stage. And then the rest of the vehicle can go re-enter and we can recover it. That's the plan. It will have plenty of heat shield on there. Re-entry is much more forgiving than exit. It'll be made out of 1/2-inch stainless, which would probably survive even if we didn't have a heat shield on it.
Right.
We expect to lose about 1 kilometer per second to drag through the atmosphere. So if our muzzle velocity is 5 kilometers per second, we expect to emerge, get to orbital altitude with something, a little bit less than 4 kilometers per second. Okay. And then we got to get up to like 7.5, 8 kilometers per second. So we'll need something like, another, 4-ish kilometers per second of delta V. That's for the slow launch versions. We basically expect that will probably be a solid rocket motor because they're relatively inexpensive. We don't care too much about performance. 275 seconds of ISP is basically fine for us. And that's low for a modern solid rocket motor.
And you think the solid rocket motor can withstand the Gs because there are examples of that?
Yeah, people have fired, artillery shells that have solid rocket motors, and those are taking 60,000 Gs. So I'm not going to say it's trivial. I'm sure that it will take, we're going to have an unusual vibration environment on launch and through ascent. So there probably will be some work to be done to make the grain able to survive those environments. But the advantage of a solid over, for example, over using a liquid is, one advantage is solids are much more dense. And that actually really helps us.
Yeah, you don't have to worry about turbopumps and all the complex machinery.
Right. And we don't expect to get this part back. So for our second stage to be, a solid, we'll probably also have some like cold gas thrusters for orientation control and fine tuning of the orbit. But that's sort of the general plan is to have something like a few kilometers per second from a solid rocket motor kick stage. At the large scales, when we get really large vehicles that are traveling at like 8 kilometers per second, we get to orbit nearly at orbital velocity. We get to orbital altitude nearly at orbital velocity. We only need basically like 300 to 500 meters per second to circularize the orbit, which is fantastic. That's a mouse fart, that'll be a tiny little solid rocket motor. I threatened my co-founder that maybe we could just do it all with cold gas thrusters. It wouldn't be great to do 500 meters per second with cold gas thrusters. It'd be too much, but that's not bad at all. If we can get the launch system to get us up to 8 and we can survive the atmospheric transit, then we get, it's a really nice system. We get, better than 50% payload mass fraction, which would be fantastic.
And you guys are somewhat stuck on a certain orbital inclination because barrel of the cannons can be pointed in a certain direction. And by the way, I'm thinking maybe a alignment with sun synchronous orbit may be strategic given the rage with orbital data centers, and they'll probably want to be in sun synchronous orbits and that sort of thing.
That's sort of the current plan. Okay. Yeah, we definitely we get our inclination is fixed based on our launch site and our orientation. One thing that we've talked about is like, well, what if somebody wants to fly to a different orbit? And basically our plan is space tugs. We will have the best system for putting fuel up that will exist, and it'll be really cheap for us. We may have to ballast existing payloads with extra fuel tanks because we want our systems to be fully packed when it launches. And so if somebody wants to put up a payload that is undersized for the payload bay, great. We'll pack in a few fuel tanks, and when we get up to orbit, we can pop those out and rendezvous with one of our space tugs and refuel, and then use that to get the payloads that don't want to be in a sun synchronous orbit, to get them out to wherever they want to go. Whether it's equatorial or some more like a 50 degrees for some communications application or something, or maybe eventually out to geo, wherever you want to go.
Yeah. And I would think you could vary the inclination a little bit by just changing your lift vector, maybe a little bit of side slip angle in addition to angle of attack. And
you can probably get a degree or two. Every little bit will cost us some amount of drag and delta V. So there is two wolves inside me. One of them saying like, we can build this amazing high performance system. Like, look at how optimized it is. And then the other one saying like, we can make this minimum viable product. Like, look at how low risk it is, and there's a constant tension there about figuring out the simplest ways to get things done versus the coolest ways.
Well, speaking of risk in your system, I spent early in my career doing trajectory analysis, some of which was for range safety purposes. So I worked a lot with range safety officials, and for you guys, I think that's going to be the FAA, correct? And you want to talk a little bit about some of this, the challenges from a range safety perspective, and
we've started looking at the requirements for a Part 450 certification, which is what you need to go to altitude with a launch vehicle, and I think the our downrange requirements are actually really similar to a rocket's. They're just sort of inverted. A rocket goes up and over, and we go over and up. But we'll need something like 100 kilometers downrange.
Cleared airspace,
basically, to do that ascent.
Lots of desert area.
There are deserts, there are coastal areas. Actually, the biggest difference that we have from a rocket in terms of like downrange environment is we're low to the ground, relatively speaking, for a large portion of that, the first 20 kilometers, say, and we're traveling at a very high Mach number.
Acoustics.
And we are a large, massive body. So our sonic boom profile is unforgiving, let's say. We'll probably have to fire out over oceans and not overfly people's houses, or we will damage their houses. I don't want to say blow out their windows.
Angry homeowners.
It's a pretty massive sonic boom that this thing will generate when we're at at near orbital velocities and near the ground. It's not not a good environment. So we're going to have to be in really remote locations, either firing out over the ocean or there might be spots in Alaska or northern Canada or something like that. And we don't care about, again, high latitudes aren't scary to us because, if we're going to be firing into a high inclination orbit anyway, it doesn't really matter. Weather matters a lot for us. We can't fire through a cloud. Clouds are like a wall of shrapnel for us.
Yeah, it's going to tear apart your TPS.
Equivalent to a flat cannon. Yeah. So we are more sensitive to weather than even a traditional rocket. But again, we're also really flexible in that, like, we can wait for things to go and we can push the button, whenever it's convenient.
By the way, when you build this, I want tickets to come to the launch, but I definitely want to be uprange of the cannon, not downrange.
Everyone will be uprange, probably in a bunker. It's I mean, I think we're pretty good about our safety protocol so far. We've never had anyone injured on a shot. We haven't gotten to start working on the really energy intensive stuff yet. Each of our pressure vessels so far has just been full of inert gas. And eventually we'll be working with combustion probably, and so those systems will get much more energy intensive, and we'll but we already have protocols in place to keep people away from everything, so that we don't get hurt. It's important.
So I think my last question or two is really just on the economics of this, right? You want to get down to even below where SpaceX is quoting for Starship, right? Yes. I mean, I think Mike is quoted as low as $10 a kilogram. Certainly not going to get there with a two-stage system. If you're able to get single-stage orbits, you could definitely drive down economics. But whether it's, maybe talk about both scenarios, right? The single-stage Mach 20 plus versus the Mach 10 version that is a two-stage vehicle, and what you think those unit economics are going to look like.
It's funny you say that, actually. So there is a very direct trade in terms of cost between the cost of solid rocket motor grain and the cost of heat shield. And so for the larger systems, they need much less solid rocket motor, but their heat shield needs to be a lot thicker. And if the heat shield is expensive, then that might more than make up for the savings on the solid rocket motor. So the cost optimization process is, like, I expect that we'll be able to make these, heat shields relatively economically, and solid rocket motors are, cheap, again, if you make them, at bulk and scale, and you can
Right.
control your processes well. So it's not totally obvious to me, which is better to optimize off the bat. And so I think there is going to be an exploration looking for the cost optimization process. So there's so we can sort of break the system out into two pieces. There's the vehicle and the ground-based accelerator, and the cost per kilogram on the vehicle. If we just said, like, what's our cost per kilogram of payload on the vehicle? What are the major drivers of that? Well, the first would be the aerostructure. If we didn't get to reuse the aerostructure, that all that stainless, that's a huge investment of, both raw material and labor. So if we get to reuse that, that's great.
Yeah.
The next is basically the avionics and control systems on board. Those are, relatively elite high performance systems. It'll be great if we get to reuse those. The heat shield is not going to be reusable.
Right.
So
sure.
that is, on the vehicle, the two things that there's no way we can really make them reusable is basically like the payload deployer bay and the heat shield, and the solid rocket motor, obviously. So figuring out the manufacturing to make those things as cheap as we can is going to drive that. And right now in some of our cost models, cost per kilogram of the vehicle, again, depending on scale, is, between $50 and $500 a kilogram. And so if we, get really large vehicles and they get really efficient, and we make some assumptions about how cheap we can make, heat shields and solid rocket motors, we can get down into the neighborhood of, less than $100 a kilogram on the vehicle side. And similarly, on the accelerator side, the cost there is basically hydrogen generation and compression, and burst disks. Those are the three things that are basically not, conserved between shots.
Right.
Oxygen's cheap, and we only use a small amount of it if we're doing combustion. So hydrogen generation, pressurization, and burst disks. And burst disks are, again, sort of it's a commodity. We think they'll be recyclable. They're just going to be steel plates. So if we spin up a nice, burst disk refurbishment / recycling process, we think we can get that cost down to like the energy cost of reforging the burst disks, which is going to be pretty low. And then the hydrogen pressurization cost can be pretty low because we actually don't need to get the hydrogen to a high pressure if we use combustion. And then we're just talking about the cost of, either electrolyzing hydrogen or pulling it out of like a steam methane reformer or something, which, if you go, high end is like $5 a kilogram, and, you can get cheaper than that. So when we are looking at the costs for the whole accelerator, again, at the small scale, a few $100s per kilogram of payload. But when you get up to the really large scale, the cost to launch the accelerator, it's entirely possible we could get the cost per kilogram on the accelerator side alone, down into the neighborhood of, $10 a kilogram. And so ultimately we think we can get a system that is, less than $100 a kilogram. And again, this is like, this is those two, wolves inside me fighting, because like, I really only want to talk about like, yes, at a 4 or 5 kilometers per second system, here's what we can do. And it'll be competitive. It's going to be cost competitive with Starship. But it's, it'll have a very different payload user's guide. We don't expect people to just take, like, we expect the first customers will be like, universities building CubeSats.
Sure.
They're going to be the people who'll be like, that would be cool to fire this thing.
Let's bring the students out and watch.
Exactly. They'll be happy to do that. And our payload deployment system, even if we're deploying like 1,000 kilograms of payload, it's going to look a lot more like a Peapod deployer than a traditional, whatever, ESPA ring or whatever, because you're going to have to experience 300 Gs in the barrel this way, then 20 to 30 Gs the opposite direction when we emerge, and you're subjected to the drag right at the muzzle, and then 20 or 30 Gs on a perpendicular axis due to the pull-up maneuver. So those are all G-load environments that a traditional satellite is not happy with. And we don't expect people to just make a quick mod to their satellite. It's probably going to be people designing their satellites for our deployer, and we'll build a deployer that makes it easy and makes it so that people can design and build things that'll launch on our system. But it will probably mostly make sense for people, for companies to launch on us if if their launch costs are a large fraction of their total system, cost. If you've got, huge amounts of non-recurring engineering expenses, and you've already got a giant, test vibe test and thermal vac facility and everything for all of your systems, and you're only building 2 of them,
Right.
and you already built 1, like you're not going to launch the second one on us,
right.
But if somebody's thinking about like, oh, I'm going to make a new communications constellation or a new, AI data center system, like my chips on my AI data center don't care about G loads, approximately.
Right.
Maybe it makes sense to package those things in these boxes that can just be popped out of these, out of a gun system. It's entirely possible. So I think that's sort of how we're thinking about the economics and the sort of the customer facing side of things, I guess, a little bit.
So I guess my last question is, for investors like me, like kind of what's the one key takeaway that you would want me to know about, either from a technical perspective or an economics perspective?
I mean, I think most of the people who are investors are concerned with risk and returns, right?
Yep.
I think those are the things that I think about. So from the risk perspective, we're not a low risk thing. There's still a lot of technical challenges ahead of us. I think that there are solutions to those challenges. I don't think these are problems that are unsurmountable.
Right. You're not violating the laws of physics.
Right.
This is a hard engineering problem, not we need to figure out new physics.
Right. Not unobtainium. Yeah. And I think we are attacking a problem that is worth attacking. We're not just going to try and put up CubeSats. We are going to try and put up megatons. Our timelines involve megatons in orbit, changing the whole way that like the economy operates, from space. So I think, yes, there are risks, but then on the return side, like when you open a new frontier and humanity's colonizing the solar system, how much would it be worth to have 1,000 new Americas? You can't put a number on it, and so, I mean, that's why I'm working on it.
Yeah. I mean, I love the vision and, love where you guys are going with it. I also kind of like the fact that we haven't even talked about the DoD, hypersonic testing market, which you don't need Mach 10, Mach 20 velocities. Your Mach 5 or Mach 7 gun is probably going to be much more competitive than the rocket sleds and other things that they're currently using for hypersonic testing. And so that's a whole nother market that...
Yeah. Great stepping stone.
Yeah, great stepping stone, and potentially a great fallback if, you can't de-risk.
For some reason it doesn't work out.
Yeah, some reason it doesn't work out. There's still a market there for hypersonic testing. So from an investor perspective, I find that attractive as,
downside protection.
Yeah, exactly. A little bit of a downside protection there. So, well, great. This has been awesome talking with you, and I've really enjoyed getting to know you over the past month or so, having some of these conversations, just going back and forth on technical topics. Appreciate you humoring all my questions. And,
absolutely, my pleasure. I love thinking about this
getting
stuff.
my brain out of human spaceflight and thin-walled rockets and into the world of tungsten aerospikes and that sort of thing.
Yeah, monolithic structures.
Yeah.
Yeah. Well, all right. Thanks so much.
Thanks.